Good morning, everyone. Are there any questions, any doubts from the previous class? How many remember what we discussed in the previous class? It was ages ago. Sorry? Markov chain Monte Carlo. Specifically, we had looked at certain properties of Markov chains, like uh, homogeneity, we looked at stationarity, etc. We looked at, and under some specific conditions, we looked at that even though the samples from Markov chain, they're obviously correlated, but we can still them use in Monte Carlo sampling, which assumes the samples have to be IID, but under certain conditions, we can use them. Right? So, given that we have today's lecture and then we again have exams coming up, I didn't want to pick up a topic which would require some continuous set of lectures. So therefore, I'm taking a slightly different topic today. I'll be talking about calibration in neural networks or calibration in classifiers and regression models. So in order to understand the concept, let's first look at the CIFAR dataset. How many of us have looked at the CIFAR dataset earlier? Anyone who's used? So it's an image classification dataset, right, primarily. The CIFAR 10 dataset has 10 classes, right, 10 classes with 6,000 images per class, and they've given the specific number of training images and test images. Interestingly, if you look at the authors' names, Alex, Vinod, and Jeffrey. Right? Geoffrey Hinton is, the Turing Award winner. Alex is the same person whom after AlexNet was being named, and this was the watershed moment. This was the moment when people started taking deep learning very seriously. So this data set is from the same set of authors. So again, if we think that top machine learning people are just giving you newer approaches, you have to think some of them are investing the time and effort in data sets also. So there seem to be 10 classes and then 10 random images from each class: automobile, bird, cat, deer, dog, frog, horse, ship, truck. And they mentioned that the classes are mutually exclusive, so there's no overlap between automobiles and trucks. Automobiles is sedans and SUVs, and trucks are big trucks. Then they have a similar data set, but which is CIFAR 100. In CIFAR 100, they have 100 classes. They've also given some super classes, so they've given some hierarchical data set in some way. You have aquatic animals containing beaver, dolphin, otter, seals, etc. Fishes containing aquarium fish, rays, shark. Then you have people containing different baby, boy, girl, man, lizard, reptiles. Vehicles they have given across 2 different categories. Right. So my question to you, having seen the data set, so let's look at the data set again. Right, let's carefully look at the data set. Right. Now my question to you is, this is picked up from a different blog. What do you think are these images? Apple. Let's assume these are apple for now. Anything more you can add? No, not in terms of fruits. Let's assume this is an apple. Anything else you can tell from these images? Most of the background is? Okay, so the background, some of them have white background, like this one, this one, this one. Some of them have some green thing in the background. This is a white background. That is something about the background. What else can you tell about this image? Very less uncertainty. If you are assuming that these numbers are probability of something. Yes.
So like in apples, we also have green apples and.
No, but that is not in this image. The question is, what do you see in this image?
Apples are of one type. Well, we should also have green apples.
Are all these red images?
Red color
Right.
is the most common.
Red is the only color here, right? Now, this particular neural network was trained on the CIFAR 10 dataset, or 100, one of them, right? And it's predicting one particular class with very high probability. What is that class? Truck. Buy a truck. There could be some fire trucks having red color. There could be something else. In this specific case, this is predicted as an automobile in all of these examples with a very high probability. Right? Why is that happening? In the training data set, we have not seen any red apples. The only thing which we have seen red in a training data set is automobiles. If we go back to the automobile class, there seem to be a lot of red things. There seem to be something in red also, right? For some particular reason, it's picking. Maybe the trucks are very boxy in nature, squarish in nature, whereas the automobiles have more contours. There's a smoother, which might resemble apples more. It's just a hypothesis. Is this a problem?
Yes.
Why is this a problem?
Prediction itself is wrong firstly, and secondly, the uncertainty showing is very low.
Okay, so good. Firstly, the class assigned is wrong, right? The class which we are trying to predict does not exist in the data set. It's an out of distribution object. Secondly, for out of distribution objects, it would have been okay if we said this is a 50% chance of an apple, something like that, or a 20% chance of an apple, or if we have 10 classes, roughly 10% for each class. But here it's saying 99.9% this is an automobile. That is bad. Right? Now imagine using these kinds of models in production settings. Right? You are driving a vehicle and someone just hangs an apple in front of you. What will happen? You'll get confused, right? Self-driving vehicle will get confused. Or if you're trying to tell, so this unfortunately sometimes happens in medical domain also. So how many of us know the operation behind how things like oximeters, etc. work? Anyone knows how an oximeter might work?
It flashes a red color laser light, and then it measures the reflection.
Okay, so devices such as oximeters, well, there are in two modes. In one mode, you send a light beam and you look at the transmittance coming out on the other side. In the other, you send a light beam and you look at the reflectance. Either way, you're trying to look at the pulsations which happen in your bloodstream. Right, when you are sending in blood, oxygenated blood, it is of slightly different color compared to deoxygenated blood, and that is being used. Now, let's imagine that I gave you an oximeter, and many of us would have used oximeters using during the COVID times. Did any of you get some scary readings sometimes? 90% oxygen or 80% oxygen, something like that? Sometimes. So some of them could be very inferior quality. One of the other reasons this could also happen is that they were poorly calibrated. They could have perhaps been tested on, let's say, a different skin tone as your skin tone, right? And because of that, it should probably say that I don't know, right? Or it should fail to report a reading. But if it gives a reading and you end up taking that as the correct reading, and you may, just go into hysteria. You may become crazy thinking that your oxygen level has dipped so much, and there are so many cases happening, right? So there are some real implications of predicting things with a lot of confidence, right? But most of the many of the medical devices, hand-end devices that we see, they don't even report any uncertainty. This was one example. Let's look at the second example. What do you think this is predicted as? What are these?
Green apple.
These are green apples. And there is one red apple also here. Again, our model is predicting them with a very high probability. What do you think the model is predicting? Okay, so Ritik probably knows the context and he's saying frog, whereas some other you don't know and you're saying other answers. So it says it's a frog. With probability greater than 0.9, right? So what is the takeaway here? Apples could be automobiles, or apples could be frogs. Is that the takeaway?
This is learning a very simplistic model. The model is very, very simplistic. Like it's just judging based on the color with a very high probability.
Okay, so maybe what is happening is that the model is only looking at certain colors and not looking at other features. That could be happening. But this is a modern day network. This is not some logistic regression, oldish, or a very simple baseline. This is a modern day, let's say a ResNet like model. The data set isn't diverse enough. That could be one takeaway. There's no Apple class, so this is indeed an out of distribution thing, but that is not sufficient, right? So even if there's not an Apple class, I would be okay with it being saying this is a 10% probability of being a frog if there are 10 classes, or 15%, let's say something around the average behavior would be okay. But 99.9% chance of being a frog where this is clearly not a frog is a problem. So this particular problem is called miscalibration. Right? The model is not calibrated well enough. And interestingly, this happens a lot in modern day neural networks. Right? So modern day neural networks and methods, they have become very accurate in predicting things correctly, but they end up being very overconfident. Right? Can we see this as an example of being overconfident? It has a lot of confidence that I'm correct, 99.9% chance this is a frog, but the correct class, but it's not identifying the correct class, right? So even if there was an apple or there was that the particular class was present, and it still gives these numbers, it's a miscalibrated model.
But suppose the data set had something like some automobiles were green, blue, and all, and some frogs were of different colors, such as there are multicolor, such as there are some species of frogs that are of multicolor.
Okay.
So if the data set contains something like that, then maybe it would look much more than simply the color, and maybe
we could have, if the data set were better, maybe we could have lesser of these problems. But you're looking at numbers like 99.9%, right? It's not just the data, it's the model itself which is being overconfident. We need to do something about it. We need to reduce its confidence. Right? Do we agree? We need to somehow tell the model to be less confident. Right? So could you tell me any other example now? Forget machine learning for a second, where there are a certain group of people who may be making certain predictions, and many times they can be wrong also. Stock market is a very, very hard example. Let's pick up something simpler. Weather, right? So we have the World Cup going on. We'll have the Cricket World Cup going on. We'll not want matches to be affected by rain, right? In Google, if we search weather Gandhinagar, it says a 1% chance of rain, 2% chance of rain, etc. It looks fairly good at this point of time. But if you were to look at New York, let's look at Friday. We have these numbers as 61%. What do you think the 61% means?
61% of the city might receive it.
Okay, there's one answer, 61% of the city might receive rain. Okay, someone else who has not studied this topic earlier. So we've been seeing this number a lot, right? 61%. How many of us have seen this number of, how many of us have opened the weather app? It says it's raining in Gandhinagar, but you look outside your hostel window, or I look outside my home balcony, there is no rain. Have you seen that? Many times this happens, right? And sometimes it's because it's happening, the rain is happening in the Gandhinagar city, it's not happening in Palace to Basan area. But the 61%, what do you think this means? Someone else? I'll ask everyone maybe then. Okay, this particular column, anyone? Any guess?
So my guess was that throughout the day, 61% of the chance that it will rain.
Okay, so Vipul says that if there are 40 minutes in a day, 61% minutes of the day it will rain, but it's a big city. So therefore, I think I used to try to answer in spatial perspective, and Vipul is looking at the temporal point. Any other guesses? Probability that it will rain is 0.6. Okay, let's assume that this is a very small area for now. So we get away with the spatial problem, that it's for a big city. Let's assume it's some specific block in Gandhinagar, right? Or some specific block in New York City. And this is for a specific hour. So we get rid of the time problem also. This is only 9 AM to 10 AM. So is this the probability of it being raining here? 0.6. Does that sound okay? Firstly, it's going between 0 to 100. So from that perspective, it looks like an okay thing, right? But how many of us have seen that 80% chance of rain and it doesn't rain that day? Has anyone seen that? We have seen that many times. Then what happens? Should we go and blame the forecast people? Should we blame the laws of probability people? Whom should we blame? They didn't say 100%, but they said 80%. And then we're getting to the point. Good. They didn't say 100%. So then they might as well just say that every day is a 50% chance of rain. Right? Safe. Playing safe.
Maybe the method that they followed, by that method, there was 80% chance.
Yeah, I don't care about the method. So let me give that also as a hint. I don't care what method they use. I am as a person, as a end product user, I just care about the number that they're giving, and I want to be factoring that into my calculation. If the chances of rain is above a certain threshold, carry a raincoat, carry an umbrella, etc. Otherwise, don't carry. I may want to think about that.
Large number of times you follow the forecast, then you won't get into it.
Okay, excellent. Can someone rephrase his answer?
So for expectation of large number of days, then repeat number of days will rain.
How many percent of days it will rain? 80. Okay. So let's look at this number 53%. Right? This would be a good probability forecast if 53% of the days where we give the forecast to 53% rain, it rains. A bit of a cyclic statement, right? Let's firstly pick up a better number. 53 is a bit confusing. 35%, right? 35%. So if we look at this particular day is 35% chance of rain and this is 36%. Let's assume both of them are 35%, approximately 35%. We keep looking at days, we keep looking at hours where the prediction of the model was about 35% rain. So we have one instance, we have another instance. We go to some other day, there is another instance. So this is over 3 timestamps out of a possible of 24 timestamps, let's say, right? So we keep looking through this for the entire year, right? Let's say that we identified about 1,000 hours throughout the year which had roughly 35% chance of a rain, right? Out of those 1,000 hours, if it actually rained around 350 times, then I would say it's a good classifier. It's a calibrated classifier, right? If it actually rains about 10 times out of 1,000, what will we say? The model is miscalibrated, and in what way? It is overconfident in this way, right? So let's overconfident, underconfident.
Depends on the value. If it says 35%, but it rains only 10% of the.
So it's overconfident, right? Right. It's overconfidence for the class rain. Right. So now do we know what meaning these particular probabilities have, right? And what might make them well calibrated? Ideally, we'll want them to be well calibrated. Otherwise, these numbers have no meaning, right? I may say 90% chance of rain, but there will not be a rain, right? Which is fine as long as it's only 10% of the days in practice where it doesn't rain, when you give a 90% chance of rain. Okay, Utkarsh has a question.
So confidence can be quantified as, in case of classification problem, it can be quantified as the entropy of all the outcomes, of all the predictions.
So let's not get into entropy and confidence like terms. Let's keep things simple for now. We are talking about the calibration problem, where we are saying that if we said that 35% chance of rain, if we looked at many number of instances where the percentage or the probability of rain was around 35%, actually it should rain 35% of the times. That would be a good classifier, calibrated classifier. We'll see why we need to look at entropy or not look at entropy. We'll try and keep things simple for now.
Can there be some other kind of non-calibration or?
We'll go through some examples of calibration and poorly calibrated things. I just wanted to use this as a motivating example. Let's now look at some proper slides for this. There is a very nice tutorial which I would be sharing here. Right? Can we agree with the definition? 70% chance of rain should be followed by rain about 70% of the time. Don't get too bogged down by the would be followed by etc. Right? Just whenever we give 70% chance of rain, about 70% of the time it should rain. Right? Similarly, now we can apply this to any 2-class problem with a machine learning classifier at hand. 70% chance of spam should mean that such emails, if you looked at a long-term trend, 70% of them would be indeed spam. We can do that for multi-class classification also. I will not talk about multi-class till the time we actually take an example. Now we will be taking a particular example to try and quantify what it means by calibration, or try and understand the notion of calibration by some quantitative methods, right? So we have two predictions, 10% chance of rain, both of them had no rain, right? Or think of this as whenever we have given a 10% chance of rain prediction, there has been no rain ever in our data set. 40% chance of rain, whenever we made such, we've made this prediction only 2 times, and one of those times it rained and one of those times it didn't rain. And we gave 70% chance of rain 3 times, we got 2 times we got a rain and 1 time we didn't get a rain. And we had just one prediction of 90% chance of rain, it was followed by rain, it actually rained that day. So let's try and answer this question. Do you think this forecaster is well calibrated or not? How many think it's well calibrated? 1, 2, 3. Is it well calibrated? How many think it's not well calibrated? Okay, why do you think it's not well calibrated?
Because the chance should be proportionate to the observations we have.
Okay. So in order to quantify such things, and it could depend on the baseline, like I could say that this is well calibrated or poorly calibrated depending on how much accuracy you want, how much calibration you want. The simplest way to do this is to create a table like this, where you have a p hat, which is the predicted probability of rain, and you have a y, which is either 0 or 1 for a 2-class problem. So we are just enumerating these 8 examples. The first 2 had 0.1 predicted probability of rain, but it rained 0 out of 2 times, right? So 10% chance of rain was slight. It was, we can say it as an overestimate, because if we look at y bar, it is 0 over 2, which is 0%. So it didn't rain any of those times when we predicted the chance of rain to be 10%. We look at the next bin. So if you notice, we have binned these examples. The next bin is 0.4, and it rained 1 out of the 2 instances. So the y bar is 50%, which is not very far from 0.4. So 0.5 is fairly close to 0.4. So it's okay, right? It is actually here, it's a slight underestimate, right? Whenever we are predicting 40% chance of rain, the actual rain is happening about 50% of the times, right? So we are underestimating the rain. For the examples, we have 3 examples where we predict 0.7, 0.7, 0.7. 2 out of 3 are actually raining. So the actual rain happens about 67% of the times. So it's a slight overestimate. We are saying these particular days, timestamps have a 70% chance of rain, where it actually rains 67% of the chance. So they are slightly higher. Final example, 0.9, 0.1. It is raining, so we have a slight underestimate.
Sir, before we say it is overestimating or underestimating, should we not say for 70% case take all a large number of days where it was 70% prediction and then evaluate its
Right. So Ritik's question is, should this experiment not be done over a large? Ideally, yes. But to keep things simple so that you can see everything in a slide, this is the same concept is being done on large. It will be done on a larger number of days. But the context should be 0.7 should correspond to 70%, 0.4 should correspond to 40%, 0.1 to 1%, and 0.9 to 9%.
why are you doing this bin wise?
Yes, we'll come on to the specific of this binning. For now, we have only 4 values, right? So 0.1, whenever we're saying that there are only 4 categories, 4 probabilities that are output that the model is giving. Either 10%, if we have only 10% probability, how many of times it rains? We have only 40% predicted probability, how many times it rains, and so on. We'll come on to specifics of why, what do we need to do about binning. We define these classes where we are talking in terms of rain. Y equal to 1 means rain, y equal to 0 means no rain. So the slight overestimate and underestimate is by the definition of, if for 0.1, if we find out that the empirical number of times it rained is 0.1, then it's perfectly calibrated. Greater than that is an underestimate, and if it comes out to be less than that, it's an overestimate. We'll look into that. But you're all asking good questions. That is how we will be quantifying something known as the calibration error or the expectation of the calibration error. So we end up creating something known as the reliability diagram. Let's try and understand this. We have two predictions of 0.1, 0.1, right? We put them here, right? Correspondingly, the y-axis, the proportion of positives that we see is 0, 0 out of 2, right? So therefore, we have a point, x-axis, the predicted probability is 0.1, and the proportion of positives in those examples is 0. Right? So we get a point 0.1 comma 0. We next look at the predicted probability is 0.4, the proportion of positive is 0.5. So therefore we get a point 0.4 comma 0.5, which is shown in this red cross. Next one, 0.7 is the predicted probability x-axis, and the y-axis is 2 over 3, 0.67. We put that over the red marker. The next one is 0.9 on the x-axis and 1.0 over the y-axis. Now, what we're saying is that a perfect classifier, a perfectly calibrated classifier would have had these numbers along this line, where the proportional of positives is equal to the predicted probability, right? That we'll call as the ideal calibrated classifier. Now, in some cases, we see that our numbers are above this line, and in some cases, we see our predicted positives, proportion of positives is below this line. Let's look at the first one. The predicted positives is below the line. Right? So what can we conclude from this? Is our model overconfident or underconfident? It is underconfident. Right? Let's confirm that. Right. 10% chance was a slight overestimate. Let's talk in terms of overestimate and underestimate for now. It will just keep things simple, as I mentioned. Our estimate of 0.4%, 0.4 predicted probability of rain was an underestimate because it rained 50% of the times and so on. But now we come on to the questions that currently we had only 4 probability values, discrete probability values which are there in the table. What if we had something different? Let's change the table slightly, but more or less it's the same. The bins I'm not changing. So the first 2 examples are still in the first bin, the next 2 examples is in the second bin, and so on and so forth. And you can see that the similar values are put in the similar bins. Right. So now we change this previous 0.1 to 0.2, we change this 0.4 to 0.3, and we change some of these 0.7s to 0.6 and 0.8. Right. Now previously, if you look at the x-axis, we took the x-axis point corresponding to the first bin as 0.1. Right? Can you think of that as the mean of 0.1 and 0.1? Now we take the mean of 0.1 and 0.1, which is 0.15, right? Which is what we plot here. Right? The x-axis is 0.15. The y-axis is the proportion of ones here, right? Which is still 0. So previously we had a point on this graph which was x equal to 0.1 and y equal to 0. Now we have x equal to 0.15 and y equal to 0. Similarly, can someone tell me the next point, x and y for this, for the next bin? X equal to 0.35, y equal to 0.5, right? So x equal to 0.35, y equal to 0.5. Similarly, for the next one, x equal to 0.7, y equal to 0.67, and for the next one, x equal to 0.9, y equal to 1. Right? So if you notice, the calibration curve has slightly changed. The reliability, this is known as the reliability diagram, is slightly changed. Now, some of you may have questions about the bins, etc. Okay. Can someone answer what might be the downside if we plot all the probability values individually? So he's saying that for 0.1 mark separately, for 0.2 mark separately. So we'll have, so he's saying that on the x-axis, we should have a point corresponding to 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. That is a perfectly valid approach because there also we are binning, but the bin is kept to be of size 1, right? Why is that a bad idea?
So then for every x point, we'll have only either 0 or 1.
For every x-axis, no, you may have, so Ritik is saying that for every x, we may have either 0 or 1. No, we could have repeated 0.1s, let's say. Bhavesh, you had answer?
We might want to average out over a range because
Yes.
like exact prediction.
Right. So if you average over a very small number of things, very small number of samples, it could just be an outlier. Right. It could just be one odd day where it seems that the predicted probability was very high, but it didn't rain that day. So you may then assign, you may say that it's very poorly calibrated. So let's imagine that we had a lot of 0.8s, 0.8, 0.8, 0.8, 0.8 in our data set, and for them about 80% of the time it rained. We had a single 0.9 and that day it didn't rain. Right? If we kept 0.8 and 0.9 separate in the graph, then for 0.8 we'll say the predicted probability seems correct, but for 0.9 it's suddenly off. Right? But instead, if we had grouped 0.8 and 0.9 into a single bin, we'll say it's probably more or less okay.
So what if we have a good number of samples for all those probabilities?
We could have them, but we will always have a consideration between how precise you want or how small intervals you want versus how many samples you get in each interval. You'll always have a trade-off. You had some question.
Between 0.8 and 0.9, then we can have some prediction.
Yeah, right. The other problem of just using the specific numbers is that this is the toy example, but the predicted probability which we saw here, for example, right? Are any of these numbers repeated to 3 decimal places? Probably not. Maybe 1 or 2, but you get my point, right? If we took a larger number of decimal points, they may or may not be repeated, right? So you can't be looking at each of the point as a separate probability value on the x-axis. Right? So we have to somehow bin these things, right? We have to. We generally don't look at overlapping bins. We look at bins which are decoupled from each other, but we typically look at equal size bins, and typically for a probability range we may look at 10 bins, 11 bins, 0.0 to 0.1 and so on and so forth.
Because if you that way, we'll have to decide how to bin them because we might have chosen some bins that might not work.
You can, yeah, right. So about binning, again, it's, you could think of it as a hyperparameter. Similarly to histograms, you have the bins, how many size you keep. Similarly in density estimation, what is the bandwidth you keep. As long as you're not purposefully designing a bin to show that your method works better than the others, it's okay in practice. In practice, I've not seen overlapping bins being used, but there are some continuous versions of this also being produced. So in this case, if we look at, if we made the bins much bigger, we have much more samples across each of the bin, and indeed it looks like we are, for both of these points, we are on the line, right? So if we look at these bins, we'll say the model is perfectly calibrated. If we looked at a different set of bins, the model does not look to be perfectly calibrated, right? So therefore, we should just choose some standard convention in the literature, right? So in this case, we choose each point as a separate bin, and you'll say the model is very poor, recalibrated here. So these bars, the pink bars that you're seeing, is the gap between the ideal and the estimated and the observed proportion of positives. And we see that these things are quite big, right? So this in fact leads us to the metric of concern, which is known as the expected calibration error, right? So think of this as we want to sum each of these, we want to sum the heights of each of these pink bars, which is the gap between the ideal and what we have observed. Is just summing enough? We typically do an expectation because certain bins may have a lot more points. Certain bins may have very small points. I mean by summing I meant average. We just don't average these. We we take an expectation by, and the weight is the fraction of points across each of the pin, right? So already now you have looked at a specific metric called expected calibration error, right? Before the start of the class, if you heard of the term, you may get a bit scared, right? Looks like a very sophisticated term, expected calibration error. But now if you see, it's quite a trivial concept. Okay, so now let's try and do this using some code. Let's try and make some reliability diagrams and calculated expected calibration error. We'll look for simple case of classification. We'll eventually go to multi-class classification, and after that we look at regression. 3 specific cases we look at. So some standard imports. So sometimes when I give assignments or I ask students to work out such similar things, one concern I have is that they typically go on to very sophisticated models. They may pick up, let's say, ResNet or some very complicated, let's say for regression, they'll pick up some very sophisticated Bayesian neural network something. But I always suggest you start off with a very simple, for classification, Make-Moons-like dataset, or for regression, a sinusoidal-like dataset, and then you verify your implementation on that before you make things more complicated. And that's what we'll try and look at here. We'll look at the Make-Moons dataset. I will look at the logistic regression data classifier from sklearn. Now my model, I'm predicting the probabilities. So for logistic regression, for k classes, they give you a vector of, and n examples, they give you a matrix of n cross k. For each of the class, they give you the respective probability, right? So therefore, just to keep things simple, I'm just looking at the probability of class 1, right? So therefore, I'm looking at all rows and the first column. So my p hats, the first 10 examples is 0.6, 0.4, 0.9, so on and so forth. Now I can also get the true labels, the true class corresponding to these points. True labels is just y, and I look at the true labels for the first 10 points. One thing which I always suggest is to make use of certain good data structures which make visualization understanding easy. In this case, it's a pandas data frame. Now if we have this data frame, can we now already apply all the techniques which we studied previously, right, to make the calibration diagram, right? To understand it better, let's take a very specific example. We want to just see around the point where a model predicted probability of class 1 to be 0.5. And we'd expect about 50% of those points to be class 1, about 50% to be class 0. Right? So what I will do is, I will choose the points where my p hat is between 0.45 and 0.55. It's a simplifying assumption. Later on, we'll do a better way of binning things, but for now, it's 0.55, 0.45 to 0.55. We look at such a data frame, and if I just take a head of this, so it ends up giving me about 31 samples. This data frame, my total number of samples was 1000, right? So about 31 samples have the predicted probability of class 1 to be between 0.45 and 0.55, right? Out of these 31, we would expect roughly 15 of them to be class 1 for it to be a good classifier, calibrated classifier. Let's see what number we get. And I'm also plotting the histogram for the p hat values, just to show in general how logistic regression makes prediction, right? Most of the points it's saying they're either class 0 or class 1, very clearly. It doesn't seem to have a lot of points in this zone, right? You can see that from the numbers also. We had 1000 points, only about 30 of them are roughly around 0.5. So the remaining 970 are either very clearly predicted to be class 0, clearly predicted to be class 1. Now we go back and try and answer this question. Out of these 31 points, all I need to do is to sum up the y vector for these 31 points, or the average out that y vector. And that is what I'll do. I'll do the sum. 18 of them turn out to be class 1. So my fraction of positive examples turns out to be 0.58. I would have expected it to be 0.5, but it turns out to be 0.58. Slightly higher, right? Now I'll do the binning. So I will be binning in bins of 0.1 and bin sizes of 0.1. And there are some very good pandas functions, like this is a function called pd.cut, pandas.cut. It will automatically put your p hat values in the different bins. You could write a for loop, but you could make mistakes, especially around the corners. But just wherever possible, use such functions. Now, I specifically try to create these things in the data frame. Now, you can very clearly verify also that for the first row, p hat of 0.608, y is 1, and it is in the bin of 0.6 to 0.7. So, if you notice, pandas clearly very nicely also bins. So, one of them is an open bracket, the other is a closed bracket, like one of them is a parenthesis circular bracket, the other is a square bracket. So, it automatically handles those cases also, and it will also handle all the floating point issues, etc. for you. Now, I can look at the different bins, right? I look at the different bins and I can do the mean of y. Right? What do you think the mean of y means for different bins? Is this the x-axis or is it the y-axis? Y-axis, right? If we go back, our y-axis was fraction of positives, right? And therefore, if we just stick to the definitions of, so if you look at, this is now the df, what we are doing is we are grouping by the bins. This is where again pandas makes life much simpler. You don't have to loop over. We group over the bins. You look at, for each group, you look at a subset of the data frame, and we look at, we'll do the mean of the y for that, which will tell us the fraction of positives for the particular group. So we can then calculate two specific things, mean predicted probabilities, right? We had, if you remember, the x point was, in this case, was the mean of 0.1 and 0.2, which is 0.15, right? So for each bin, we can calculate the mean of the predicted p hats, right? And that is all we need to do here. We calculate mean predicted probability is equal to df.group by bin. For each bin, you look at the p hat, find the mean. Fraction of positives is you group by mean, look at the y value, which is either 0 or 1, find the mean. Now, we should also be looking at the bin sizes. If the bin sizes are all equivalent, we could just simply take an average, right, as the expectation, but we can't do that here. So, we'll, as expected, most of the examples are in the 0.0 to 0.1 or 0.9 to 1.0 bin. So, model seems to have a lot of clarity on these points here at this point. So, then we calculated this particular term known as expected calibration error. Again, let's just literally open this up. You first find out the calibration error. Right? The calibration error we said was the difference between this particular line and this particular point. Right? So, we look at the difference between mean predicted probs minus fraction of the positives. We weigh that by the size of the bin. We calculate the absolute value because sometimes it can be above, sometimes it can be below. So, this particular thing is for the into bin size by length of df is from the expectation operator, and this is just the difference between these quantities. And if we do that for this example, it comes out to be 0.036. We can also just plot between mean predicted probabilities as the x-axis and fraction of positives as the y-axis and get a figure like this. So, the y equal to x line shown in the dotted line is the ideal case, right, where the fraction of positives is the same as the predicted probability, the mean of the predicted probability across that bin. For certain cases, we see we're over the curve, or certain cases we see we are slightly below the curve. Any questions? So, I did all of this manually. I think we should all do such exercises manually and then use inbuilt functions from Torch or sklearn, etc. because they will handle the corner cases better, but we should do it at least once to get good clarity on the concepts. So, now I will show that if I were to indeed use calibration curve function from sklearn with n bins equal to 10 and strategy being uniform, it gives me that prop true, which I get using calibration curve function from sklearn, is the same as what I found out as fractional positives. So our implementation is verified to be correct. Similarly, prop pred is the same as mean predicted probability. So therefore, going forward, I should just be calling this calibration curve method from sklearn, and then I can create a pandas data frame on this, right? Which would be something like this: probability true, probability predicted, right? Then I wrote a certain function to create the liability diagram for. So then I wrote this function to work across different classifiers, because that is what you want to see: is my random forest better better calibrated compared to my logistic regression and so on. You don't need to worry so much about the particular function. But if we look at this diagram, right? So one of the right hand side curve I am getting from sklearn. The left hand side I am using sklearn's calibration method to get hold of these x axis and y axis, but the remaining things I am doing on my own. I just wanted to show that we get the same things, right? So the first one is, so this is in the order of logistic regression, random forest, support vector classifiers, and k nearest neighbors. Logistic regression, random forest, support vector, and k nearest neighbor. What do you observe?
Linear regression one is
The logistic regression one seems fairly good, right? One interesting thing you can notice is that for logistic regression one, you seem to have the predictive probabilities across different bins. Do you see that the case, that to be the case for random forest, support vector, classifier, KNN? KNN seems to have only 4 points. Why is that? It is not predicting. So if you were to look at the histograms of the predictive probabilities, many of the points are not falling within a lot of the bins. So a lot of the bins are just empty. Right? They don't have any point on the x-axis. Correspondingly, they don't have any point on the y-axis. Yeah. So we sometimes have some contradictions. Right? We would have expected the EC to be lower for logistic regression. It seems to be better, right? But you have to also factor in that EC also looks at the fraction of points across different bins, right? You could, so let's assume that you had certain error here, right? 0 to 0.1, but that error would be inflated by a very large number of samples. Whereas while some of these look pretty bad here, but let's assume that the mass is mostly here or here, and here they have 0 error. So the expected calibration error will turn out to be lower. You can actually go and verify these things across the bins, but you'll have to do a detailed lookup of this experiment. Everything else is the same in the plots. So you have to also look at the histograms. sklearn also has a very good example on this. Okay, does this help? The histogram of the predicted probabilities. Support vector classifier seems to be like confused here, right? Most of the examples are predicted to be mean predicted probability of 0.5, whereas logistic is U-shape, naive Bayes is even more U-shape, random forest is somewhat between logistic and SVC. I don't know what this data set is. I don't know what this particular data set is. It will depend on the data set, it will depend on a lot of properties. So again, no free lunch theorem. We can't say that one particular method works better for classification. All we're trying to say is now that in addition to computing the accuracies, you should also be computing the expected calibration error, right? That will define the trust you can put in the specific model. So would you be able to put trust in deployment setting on any of these models, even though their accuracy may be very high. No. So therefore, this calibration error is a concept that we can apply, and we can compute this in addition to the other metrics that we're doing. Other questions?
So we need core of cycle and input important calibration. So there is a parameter called strategy. What could be other?
So the strategy is said to be uniform. What could be other strategies? Look it up at your own time. They could be a non-uniform. It could be based on, like, it could not do uniform bins. Currently the bins are 0.1, 0.2, 0.3, 0.4, 0.5. It may not do uniform bins.
So they are using for
You should look it up. I won't answer this. This is an implementation question. You should look it up. It will be interesting to see how that changes things. Then the lower models are better. What do you mean by lower models? In terms of expected calibration error, whichever is lower is better. If we have done things correctly, that is another big assumption. You should verify these things on your own also. Seems to me that the implementation is correct, but you should verify. Okay, other questions? So till this point of time, we were dealing with simple things, two-class classification. Now we change to multi-class classification. What changes? How do we create a calibration curve for multi-class classification? That's to keep things simple, you could think of 3 class for now. Iris dataset or something like that. Okay, one at a time.
Do the calibration per class.
If you do a calibration per class, but is your model still giving you 3 outputs or something else? You may want to then modify the model to also become 1 versus rest. You could do that. That is one method. Other methods? Other thoughts? You have 3 classes. But then it's not positive. It won't be called positive. You're almost there. Accurate. Like, accurate is not the same as positive. But it's just defined differently. That's another notion. Anyone else has any thoughts? We've looked at 2 different notions. I'm happy that you are coming up with these answers, because this is the 3 methods indeed, which there's another method which you could use, which is slightly more complicated. Again, we go back to these slides. We can, while defining the calibration for more than 2 classes, we could look at 3 things. Confidence calibration, which considers only the highest predicted probability, and then we do as the way we are doing, but we replace the fraction of positives with the accuracy in that specific bin for that class. We'll look at it in a second. Class-wise calibration will look at 1 versus rest. Multi-class calibration will want to look at the entire predicted probability vectors and not just the specific highest one. We'll not look into the multi-class calibration now. We will be only looking at confidence calibration for now. Right, this is the definition. Among all the instances where the probability of the most likely class is predicted to be C, the expected accuracy is C. That is it. Right, so this definition goes back to the 2-class definition. You could use the same definition there where we had fractions of positives. Right. To understand this, let's again go back to our data frame. I prefer looking at this. Now we have a 3-class problem. I'm again using logistic regression. I will get my predictions from my model and I put them in a data frame. My data frame at this stage looks something like this. Probability of class 0, class 1, class 2. Now, can I figure out the class with the highest predicted probability? Right? Do an argmax over the rows. So I'll do that. Again, as simple as these things look, I would highly encourage you put them in the table, put them in the data frame. Don't skip those steps. I also look at the predictions. That is just from coming from the data set. So at this stage, if I just put the predictions, it's a class 2, 0, 2, so on and so forth. I can now figure out the most probable class, which is just finding out the IDX max. And if I now look at my data frame, it looks like this. For the first example, the predicted class is 2 because that's the one with the highest probability. For the example ID 1, the predicted class is 0, which means our y hat is 0, and y is the ground truth. Sorry, I should have. For each of them, for the second, third, and fourth example, it's 2, 2, 2. Now, what should we do in this data frame? Let's pick up another point. Let's firstly make things right. So I have now changed. Okay, so I have created a data frame to include only the most probable class probability and whether the prediction was correct or wrong, because that's all we need. So what I've done is I've removed all the irrelevant columns and I've just told whether y equal to y hat or not. Right? This particular column just tells y equal to y hat for all the examples, and this one tells the most probable class probability. Now this is irrespective of the class. So this will be true for 1 equal to 1, 2 equal to 2, 0 equal to 0, and this will be false for all other cases. Right? So that is why this is, if we go back to this set of slides, they mention that we have these different notions of calibration for multi-class, and they become stronger as we go down this. The first one that we're looking at, the notion of classification, we are just looking over all the classes in one go. So it's a weaker notion of calibration for multiple classes. So we now do the same thing now. We now look at this table and see how many trues and falses we'll get corresponding to each probability bin level. So I took it at 0.45 and 0.55. Again, we're binning between that. If we do that, we get a data set which would look like this: 0.53, 0.53, 0.51, 0.53, so on and so forth. And some of them are true, some of them are false. Some of them are correctly classified, some of them are wrongly classified. I want to be looking at the ratios of these. In this case, it turns out to be 0.483. So the ratio is fairly similar to 0.5. So therefore, we'd say it seems to be well calibrated for this particular point, for probability 0.5. We can do the same thing now. We can do the cut across the different bins, and we'll get the most probable class probability. This is the samples across them. We do the same thing as before. Right? Now we've converted into an equivalent problem which we've done earlier. So we can calculate the expected calibration error, turns out to be some 0.016. I can make the reliability diagram as I've made earlier. Right? Nothing new here. You can also make the histogram of p hats and all these things. Any questions in multi-class classification, calibration? Okay. Now we come on to the third topic, reliability diagrams for regression. How will we do that? Classification was easy. Right? We get predicted probability vectors, and you can see what fraction of them are true or false. What do you do with regression? You can calculate errors, but what do you do with errors? You can bin the errors, you could do things, but you'll want to see, you want to get a notion of fraction of positives in the regression case.
You can give out intervals and you can calculate how many percentage of points are actually lying.
Okay, this is cheating because they're working on a project which already has taught them this thing. The others who have not worked on a project which already gives them this answer.
We could have a threshold on the error.
You could have a threshold on the error. You're now trying to discretize the continuous problem. You could do that. The hint is intervals. Or think about normal distribution. Think about its PDF, something like that. You can have percentage errors. You're again sort of making the discretization of that. Okay, let's look at this article to get a sense of. So today specifically I didn't make slides. I wanted you to see that these supposedly very sophisticated looking papers, very difficult looking names, These just boil down to, many times they just boil down to additions and subtraction if you know code well enough. So this is a paper which says that because of model misspecification and use of approximate inference, Bayesian uncertainty estimates are often inaccurate. For example, a 90% credible interval may not contain the true outcome 90% of the time. This is the hint. Right? So we know the credible intervals for something as simple as a normal distribution. Right? If we have a normal distribution, how much percentage of the points do we expect to be within certain sigmas? We know those things. Right? So what we're saying is, if we now look at this particular graph, right? Do you think this is a good prediction? The above one? We have the mean prediction and we have the uncertainty estimates around that. Is this a good prediction or a bad prediction? You can say from two perspectives. One is the mean squared error, the other is calibration. Forget about mean squared error, just talk about calibration. I have also written, so they have also written something like raw 90% confidence intervals.
So this is, in terms of both, this is not a very good prediction.
Okay, explain.
Because the predicted value could be expected to lie in somewhere of middle of the shaded region, and the true value significantly deviated from that, and the confidence interval which they have shown, it is a 90% confidence interval, but the true value is totally outside that.
Okay, excellent. So all we're trying to say here is that now you have these ground truth points, point, all of these blue dots are ground truth points. 90% confidence interval should be able to capture about 90% of these points. That is all you need to know here. In the bottom one, does it seem to be the case? We have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. 9 out of 10 points are falling within my 90% confidence interval. Right? Does it seem reasonable? It's again a different question of how we get that credible interval, confidence interval, which we'll see in a minute. But does this definition look correct? So now it's a natural translation to what we did in the classification case. But here we have slight different things, because now for certain models we hold the control over what confidence intervals we can look at. So I'll be looking at this particular data set now. I'll be fitting, just for the purposes of illustration, I'll be looking at a very poor model. I'll be looking at the Bayesian ridge, and I'll just fit this ridge to this data set. And my predictions would be like this. This is the mean prediction, and then I have, so my regressor gives me the prediction as well as the standard deviation. Right? For now, you just look at this, that you are getting the standard deviation from some specific model. Now, it could be coming through your Bayesian neural network or just your heteroscedastic likelihood, whatever. But importantly, your model is giving you that mean prediction as well as the standard deviation. Now, do you think this is a good predictor from just mean squared error perspective? No, it's not able to capture the trend. It is a very biased model, right? What about the calibration? So I've said I've plotted between mu and plus minus 1 sigma, right? And we'll assume that the distribution is a normal distribution. Right? What does 1 sigma in normal distribution correspond to? 60, 67, 68, some number like that. So would it be fine if we had about 68% of the ground truth points within this 1 sigma? Would it be called, would we be okay with saying this is a decent calibrated plot?
Yes.
That is all there is to this, right? So within 1 sigma, we'd like to see about 68% of the points. Within 2 sigma, we'd like to see about 95% of the points, and so on. We can see how many points are within k sigma of the mean. Right? So all we need to do is to look at where the y minus y pred is less than k into y standard deviation, the absolute of that, right? Because it could lie above or below. So for k equal to 1, we get about 5.589, right? Within 1 sigma, we would have expected 0.68, but it's 0.59, so it's slightly different. For k equal to 1.2, we get 0.755. So it seems to be jumping quickly. For 2, it's jumped up to 0.98. For 2 sigma, we would have expected to get about 0.95, but it's gone up to 0.981, right? And this is what I've plotted. For different values of k, where I'm doing mu plus minus k sigma, I'm trying to look at how many of the fraction of the points should have are falling within k sigma of the mean. As expected, as k becomes larger, for a normal distribution, your span becomes very large. You're able to capture almost all of the points, right? Which is expected. At some reasonable value of k, you will get the fraction of positives within k sigma to be 1, right? But we are talking about not in terms of k, we want to be talking in terms of what that k sigma represents, right? How much of the mass it represents, right? So we need a function to map that k sigma to that credible interval, and from that we can then say that how many of what fraction of the points are we falling into, right? Again, this is homework for you. Why are we using this particular formula? What does norm do? What does PPF do? Why are we doing 1 plus Ci divided by 2? Okay. Homework. 0.95 gives you 1.96. Does it make sense? 0.95 should correspond to roughly 1.96 sigma, right? 0.68 should correspond to 0.99, 1 sigma, roughly 1 sigma, right? So it seems to be working correct. Is there any other value we can check to confirm? Huh? 98, that gives you, so we can look at the okay, anyway, way too many ads, but seems to be correct. You can verify that. 9987, roughly. I mean, there could be something wrong either in the code or in your definition of 0.9987. It should be. So the other thing you'll see is that you get 0.68, you get 0.99. You'll see a very, very quick jump in one of these numbers. Like here, you're just going from 0.95 to 0.99, but it jumped from 2 to 3.2. You just go from, right, let me change this to 0.92. You've gone from 3.2 to 3.35, right? So here you have just changed in 0.0005 and here it's changed to 0.14. Right? You'll see that the change is much larger. Again, figure out why. You should know that. We use this function. We now get the C to K for the quantiles. Right? The quantiles we get, and correspondingly we can get the K sigma values for each of them. And then all you want to see is how many fraction of the points are within that K sigma. That is it. And we end up getting something like this. Right? So here I've done for percentiles equal to 0 to 100 in gaps of 11. And because it's a regression case, I can like arbitrarily choose any number of, like again, smaller bin sizes have certain problems, but I could have changed this number also. Let's change this to 21 and see what changes. I can change this to 1000. But let's keep it to something reasonable which most people will use. Okay. Is our model overconfident or is it underconfident? I will ask this now. Let's focus on this region for now. Right? In this region, we would have expected about 60% of the points to lie within this corresponding Ci, right, 0.6 Ci, which would have expected, but only 40% of the points are lying within it, right? So it means that our sigma that we have chosen is probably smaller, than what it needs to be, right? Which means that our model is overconfident. Right? It seems a little counterintuitive. Let's go over it again. For CI 0.6 or 60% CI, you would expect about 60% of the points to lie within that credible interval, but it turns at only 40% of those points lie, which means that our sigma is probably smaller than it needs to be. Sigma being smaller means that our model thinks I don't need to give you a lot of uncertainty, I'm very sure. Right? Sigma large means that I am very unsure. So that is all I had for today's class. Based on these reliability diagrams, we can understand if the model is underconfident, overconfident, perfectly calibrated. And it also gives us an addition metric which we can report over just giving the mean squared error for regression or just the classification accuracy, F1, precision, etc. for the classification problems. The notion of calibration we have seen is important for various applications, including weather one. Like we would be very frustrated if it says, but it's also important to understand that it's 90% chance rain. Now what it means, we should be clear. Like we should not be blaming someone if they said 90% chance of rain and it didn't rain today. As long as historically it rained about 90% of the times, right? Because that's what they're aiming to do. Now, we have looked at the problem of models being miscalibrated, right? Now, there are methods which make them well calibrated, right? Which will say that let's look at these curves, these reliability diagrams, the red curves that I'm seeing. Let me try and do some transformation so that they become as close as possible to the black dotted line. And we can learn this transformation mapping also between the red and the black using certain kinds of methods like isotonic regression or some sigmoid flat scaling. There are a few. We'll see if we cover them in the next class or we leave it up to you. We'll have to decide that. Okay. Anything else? You had a question? So the question is, should we be caring only for 90%? I was just taking as a specific example because I would personally not care about 20% chance of rain, 30%. You wouldn't be that much worried. But at 90% chance of rain and it doesn't rain, you will not be happy. Or 10% chance of rain and it rains, you will be unhappy. So to talk about the calibration, yes, we make this reliability diagram and we cover all the ranges. But I was just speaking as a human, sometimes we don't perceive all the ranges of values equally importantly. I would be frustrated if it's like you'd be frustrated if you gave a very good JEE exam and you gave or GATE exam and you got a poor result, right? Similarly, like it's the problem of calibration. Other questions? The question is, do we need to leave a validation set for this? We need a validation set. We typically evaluate the model calibration on the train set as well as on the test set. And if you want to calibrate the model, if you want to make the red curve as close as possible to the black curve, you will have to keep a separate data set. Similar to cross validation, we call it the calibration data set. And on that, we are able to try to get the red curve as close as possible to the black. On test, that may still not work out to be correct. We'll see when we study that specific topic of calibration, if we study that topic. Okay. Other questions?
So the model is poorly distributed by the sigma we are making, right? So all this calibration is good only when if the model is giving good results.
So we should ideally have good models as well as well calibrated models. Sometimes what happens is that your models can be very accurate but can be poorly calibrated. So there we can use some calibration methods to improve the calibration, to assign a proper meaning to the number 0.9, right? So and you'll see this on Twitter and social media, sometimes a lot of us, when we think of predicted probability as being 0.9, that's actually not the predicted probability. I mean, that's not the true probability, right? That's not a calibrated probability. That is what I say. So we should be very careful with when our classifier says 90% chance of cancer, 90% chance of COVID. We need to get a sense of whether that number is calibrated or not. Otherwise, we can't think of it as a probability. Okay, thank you. We will meet on Monday then next.